All right, 4.3, we're kind of shifting gears a little bit. We're going to be taking a look at something called vectors, and I mentioned this before we got started today already. There's a little bit of vocabulary up here at the front to talk about what vectors do for us, what they are, but it all hinges back on the trig in a minute. Okay, so just bear with me with like the sort of the definitional stuff that we have to do at the beginning. If you're writing your notes from scratch, you're gonna have a bit more writing today, okay? If you're writing and filling them in, you can still fill in blanks. All right, so to start with, a vector is a quantity with both magnitude and direction. Okay, magnitude and direction. So we not only have, magnitude means size, if that's a word you're not familiar with, and direction, of course, means like physical direction, right? How in this case, we're gonna be looking at angle measures typically. Vectors are generally written as arrows, where the magnitude is represented by the length of the arrow, and the direction is represented by the arrowhead. So we have things that look kind of like, I'll change my tools, this. That's a vector. You see vectors used sometimes when people talk about weather, direction of wind. You see vectors used when people talk about contours of like the steepness or the slope of terrain, like mountain ranges, things like that. You can see how steep something is. Long vectors means that they're longer, or it's more like if you think about how quickly, or we'll do the mountain range one because that one's on my mind. Short vectors usually indicate that things are going up very steeply, and long vectors mean as it's over a span of a longer distance. Every vector has an initial point and terminal point. So the vector I've drawn below, this would be the initial point, and this one where the arrow ends is the terminal point. I know I have a few of you writing, so I'm going to just take pause for a second while you do that. Okay, can I go to the next one? Are we good? Yeah? Okay. All right, a little bit more on this whole front page that I've got, which is about 1, 2, 3, I think 3 more slides. It's got a bit of writing still on it. The zero vector is a vector with magnitude 0, so it's got no size and no direction. It's very exciting, the zero vector. You'll notice a few things, and let me mention them. When you see things written in type, right? Like this is typed on my screen. Vectors are generally drawn in bold. So do you see how my 0 looks like it's extra thick? Okay, that's on purpose. Whereas you see the 0 that's underlined like over here, just looks like a normal 0. Okay, so this is what we would consider just a number, or we call a scalar, whereas over here, this one's a vector because it's the thick version. When you write it, that's kind of hard to do if you're actually writing it out in pencil. So we're gonna have a different notation for that, so hold tight to that. But I just want you to recognize that in print versus in your own handwriting, they look a little bit different. Two vectors are considered equal if they have the same magnitude and direction. Now, that sort of seems obvious, except that what that actually is telling you is it doesn't matter where they start from and where they end. All that matters is that they're the same length, size, magnitude, those words all mean the same thing, and they go in the same direction. Okay, so you can kind of imagine, let's say, that somebody's driving, well, let's do running, because then we can talk about a shorter distance. So if you were running straight east for 3 miles, and you were in Shawnee, and you were running straight east for 3 miles, and you were in Oklahoma City, then your vector, right, would be the same. It went the same direction, the same length. Okay, are you with me on that? That's a little different, right? That's not the same as how we think about some other quantities. Okay, the location doesn't matter. And then given a vector v, the vector negative v means it's the same magnitude but in the opposite direction. So again, if we use my same running analogy, if I went east 3 miles running or I went west 3 miles running, because those are exactly opposite directions, one would be a negative of the other. Okay, so the negative indicates direction in this sense. It does not indicate size. We can't go negative miles, right? You're not running negative 3 miles. It doesn't work that way. But the direction is exactly the opposite direction that we discussed before. Okay, so we're good so far. All right, here's the stuff where it's just so very friendly. Oh, I feel like I'm missing a slide. Do I have it in the wrong spot? Or I'm still missing it? It's still missing. Okay, let me write it in. Oh, maybe I put it here. I'll write it in here. I don't know. We're doing adding vectors. That's the one I want, and then we'll go back to the one that I skipped to. I'll get it put back in later. Adding vectors. So adding vectors, to add two vectors, and let me actually show you what it looks like when you write it in, because now I'm writing in, I'm not typing. So the way we would write our vectors is like this. Okay, they have a little line on top of them. Sometimes you see it drawn sort of with this one arrow kind of thing. Sometimes it looks like a full arrow. I don't really care which one you use when you're drawing them out, but just so you know, I will tend to do that because it's quicker for me to write. So vectors v and w. Place the initial point of w at the terminal point of v. The resultant vector, that means the vector that results. So the resultant vector, which is v plus w, has the same initial point as v and the same terminal point as w. And this just begs for a picture, does it not? All right, so we're going to take, draw yourself a vector and call it v. So there's my vector v. And I'm going to draw a vector, and I'm going to call it w. Okay, so I've got a vector v, and I've got a vector w. Everybody good with that? Okay, so literally what it says is to take vector v. So I'm going to do this over here on the side. Here's my vector v. And then to take vector w, and to put vector w on the end of vector v. You just attach it. Okay, so this is kind of like what happens when you drive in one direction or run in one direction and then you turn and you go in a different direction, right? That's what's going on here. And the resultant vector, I'll change colors even, has the same initial point as v, which means it's down here, and the same terminal point as w. So this piece is v, this piece is w, and this piece right here is v plus w. Okay, does that make sense? So again, if you think about directionally what happens when you're walking along roads or driving along roads or sidewalks or something like that, we do this all the time, right? You're tempted to go across the grass where the yellow is, but somebody put a sign that says keep off the grass, and so you're trying to obey the rules, right? But the result is the same thing. You end up at the same spot. You started from the same place. So let's talk about subtraction real quick. To subtract vectors v and w, note that v minus w is actually the same thing, of course, as v plus negative w. Makes sense, right? But what did we say negative vectors do? How are they related? They're the same size, but what does the negative do? It reverses the direction, right? So if you were going east, now you're going west. Is that what you said? Sorry, I couldn't hear very well. You're being very quiet because I could tell you were a little unsure about your answer, but that's okay. All right, so up here, I'm going to use my same vectors v and w. So this one right here, v. Oops, I didn't mean to cut it. Let's copy it. So here's vector v. And then up at the top right there was vector w. So I'm going to show you what it looks like for you to have a vector that's negative w. So I'm going to shift this over. So negative w, we'll draw it in orange, would look like this. Does that make sense for everybody? It's the same size, at least if I've drawn it well, which I think I've done okay, but it's going the opposite direction. So we do the same thing, it's just that we use the negative w vector that we touch to the end of the v vector. So we're going to take that negative w vector and we're going to put it at the end of the v vector so it'll look like this, right? And then our resulting vector would be right here. And this one, so this is v, this is negative w, and down here we have v minus w. Okay, everybody good so far? Remember, we're just talking about directional things. So if you can think about running or driving or something like that, you have a pretty good picture in your mind of what the vectors are doing for us from the perspectives that we're looking at the moment. Okay, let's flip back to my slide because this one was missing where we left off, which was properties. So there's some really good properties for vector addition, and there are a lot of the same properties that you know from real numbers. You probably don't remember all the words for them, which is okay. Commutative just means the order doesn't matter. So if I start with v and then I go to w, or I start with w and then I go to v, it's the same thing. Okay, and I'll draw you a picture for these to show you, at least a couple of them, to show you that this makes sense. Associative says that the order in which you do this doesn't matter. So if I add v and w first and then add the u vector third, like second or whatever, second I guess, or if I add w and u first and then v second, I'm going to end up at the same spot. And you kind of know this, right? Like if I'm trying to go from here to Shawnee Mall, there's more than one way to get there, correct? Yeah, I mean, you could go east and then, or you could, yeah. Yes, east. You could go east and then you could go north, or you could go north and then you could go east. It doesn't matter which one you do. That's a commutative idea. If you take side streets where you make a lot of turns, same idea. Zero vector, excuse me. When you add a zero vector to something, it doesn't change it. That should make sense because zero has no direction and no size. Of course, it's not going to change anything, right? Yeah. And inverses. Inverses say that when you add something to its opposite, you get back to zero. Right, so imagine you ran 3 miles east and then you turn around and ran 3 miles west. Hopefully you're back where you started. I mean, like that's what that would be doing for you, right? Yeah. So let me just show you from the perspective of the v and the w that I drew a minute ago. Let me copy them though because I didn't have them copied here. I want to do this v and this w here. Because I think the first one's really easy to show. So we're going to look at v and w and then I'm going to show this commutative property here. So what we had said before is that if I wanted to do v plus w, we would do v, and then we'd do w, right? And it would look like this, with the line between it right here. Whoops, let's try one more time. There we go. Okay, so this was v, this is w, and this is v plus w. Now, let's do it the other way. Let's do w and then let's do v. So we're going to start with w. So here's w, and then we have v. It's going to be on the end of w. So it looks like this. I'm running into myself, so I'm going to shift it down here. Oops. Try again. Okay. And then if I do v plus w, or sorry, w plus v, it would be over here. So this is v here, sorry, and w there. And this one would be w plus v. And I'd like for you to compare, just visually, these two. That'll be first. Compare these two. Remember, vectors are the same if they have the same direction. Are those two yellow vectors the same direction? They seem to be, right? They do. And the same length. Are they the same length? They seem to be. And if we actually moved them closer together, we could actually verify that. So if I moved this, for example, over here, closer to this, look at them. They're the same. They're a little bit off because my tools are a little bit off, but you have the right idea, yeah? Okay. So that would be showing you sort of a picture of the commutative property. All right, scalar multiplication is next. So scalar is just a quantity that involves magnitude but no direction. The second bullet's a little bit more clear even. It's just a number. A scalar is just a number. Just a number. We can multiply a scalar k. Notice when we multiply it with a scalar, this is not boldened, right? It's just the normal k. They do sometimes like to make it an italic kind of look to differentiate it, to make it clear for you, so you'll see that happen too. So we can multiply a scalar k by a vector v to get a new vector kv. Okay? The scalar multiple, which has the following properties. So if k is positive, the direction of kv is the same direction of v. Right? If we do whole number values, it works pretty well to think about it, right? So like if I ran 1 mile today in one direction and I want to do double that tomorrow, scalar multiple times 2, I would be going the same, and I want to do the same route, right? I would go the same direction and I would be going twice that far. If k is negative, the direction is opposite. That makes sense because that's what we said negatives did. They switch direction. And if k equals 0, or if the vector equals 0, that actually should be a bold vector, and it's not. I'll fix that later too. This is a bold vector. I'm putting it in yellow to remind myself. So if you have the vector is equal to 0, which also should be bold, then kv is 0. So when you multiply 0 times something, you get 0. Okay. All the properties that we see from whole numbers, again, you may or may not remember all their names, they show up inside of vectors as well, because vectors really are magnitude, which is size, hence numbers, and direction. Now we get some extra properties here in a little bit too, magnitude showing up here in a second, but so far all the properties that you've seen are properties you've seen before. All right, this next one is new. Okay, so we talk about the magnitude versus the angle measures here in the next couple of slides, I think, at least this one for sure. All right, a vector's magnitude or its length is denoted by having double bars, so it's kind of like absolute values, but they're double on the sides when we look at it. And this is telling us we're just caring about what the size is. Okay, magnitude means size or length. So some properties about magnitude. The first property is that magnitudes are positive or 0. That should make sense, right? Again, think about what happens when we're talking about a running example. You can't run negative miles, right? The distance is always minimum 0 if you don't run at all, or it's positive. The second one says that the magnitude is 0 if the vector is 0. Well, that makes sense. If the vector is 0, then its length is 0. That's the only time that would happen. If you have a negative directioned vector and you take its magnitude, it's the same magnitude as the positive direction vector, right? So if you run 3 miles east and you run 3 miles west, one of them would be considered a positive vector, the other one by comparison would be considered a negative vector, but their lengths, their magnitudes would be the same. Okay? The next one says that when we multiply a scalar by our vector, we could just find the magnitude of the vector and then multiply that by the scalar value, whatever it is, 2 or 1.7 or 0.23, whatever it is. And the last one, and we will see this show up again later as well, is about unit vectors. It will show up in the next slide, in fact. If the magnitude of the vector is equal to 1, then the vector, this should also be bold. You don't notice typos until you start reading through them with you guys. So thank you for helping me out find my typos. This is called a unit vector. It's just a vector of length 1. Okay, we have one more slide of definitions before we get some examples. That'll be much more exciting, or at least, something more to do than write things down. Okay, one more slide. Can you bear with me with one more slide? Absolutely, you guys are doing great. All right, here's our last one. This is describing vectors in the rectangular coordinate system, which is what we will see used a lot. All right, we're going to use vectors I and j. And in Calc 3, just so you know, and in physics as well, they introduce a third directional vector, ij. What comes next? K, and it's for the third dimension, right? So all of our dimensional stuff is going to be flat, right, in a coordinate plane. But when you extend this to 3 dimensions, all the properties we've actually talked about are still the same. But we're going to do 2 dimensions. So the vector I is the unit vector along the x-axis. Okay, so I'm sorry, I drew my hand in the wrong direction. The x-axis like this. Okay, it's how far left and right you go, right? That's the x-axis. And then the vector j, is the unit vector whose direction is along the y-axis, up and down. And one of the ways you can remember is that it's alphabetical, right? X and then y, I and then j. Okay, so that's one of those things. A vector can always be written in terms of its components, kind of like an ordered pair in space. So a vector v can be written as ai plus bj. A is the horizontal component, how far left and right you went. J is the vertical component. I'm sorry, I said that wrong. B is the vertical component, how far up and down you go. The I and the J tell you that you are moving 1 unit in that direction, and then when you put the number in front of it, it magnifies it, right? It's a scalar multiple. Here's the cool thing. The cool thing is that everything that we have established so far is nothing different than you've done before, and you're about to feel like you're back in Algebra 1. Who wants to go back to Algebra? No, you don't really want to go back to Algebra 1, but you're not too terribly concerned about your abilities to do it. It's been a while, but you know how to do this stuff from Algebra 1. So let me show you what this looks like. Oh, sorry, a couple people still writing. I'll pause. Okay, are we good? You good, David? Okay. All right, examples. There was the slide I added in. Okay, some examples. We're going to sketch the vector in a standard position vector and find its magnitude. All right, so here's the way this works. Just draw your normal order, XY ordered coordinate plane. So you're going to draw XY axis, roughly speaking like that. And what this is actually telling you is that this is how far right or left you go, and it's 5, and it's positive, so we're going to go right. 1, 2, 3, 4, and 5. And the next number is how far up or down you go, and it's negative, so we're going to go down, and we're going to go down 2. So we went right 5, down 2, and we end here. This is the ordered pair that's represented by this. Everybody good so far? And to sketch the vector literally means that we take the origin as our initial point, and that point right there is the terminal point, and that's it. Okay? The 5 and the negative 2, that should say negative, tell us the direction that we go from wherever we start, and we get to start wherever we like, so we might as well start at the origin, right? Now, finding the magnitude, what it means is finding the length of that yellow piece. Do you see something that you can use to find the length of that yellow piece that you have been using off and on, at least, all this semester and many semesters before this one? Pythagorean theorem, or you might be thinking distance formula, right? There's a triangle there. Do you see the triangle? All right, you can either draw the triangle up to the x-axis or over to the y-axis, doesn't really matter. But the triangle that we have here, let me do it in orange. The triangle that we have here looks something like this, right? And the length of the orange piece is going to be found by the Pythagorean theorem. So this is 2, and this is 5. So if I want to do this, this is the square root of 5 squared plus 2 squared. What is 5 squared plus 2 squared? 29. So this is the square root of 29. It's just the Pythagorean theorem. What do you think? That's the magnitude. Yeah, and we didn't have a vector name given to it, so we'll just use the 5i minus 2j. Notationally, what it would look like then with that notation is that it would look like magnitude 5i. And sometimes they do I hats like this in other books. Your book still just uses the line on top of it like that, the arrow on top. 5i minus 2j is this. That's the magnitude notation. So if it's asking you, or if you're seeing that notation, that's what it would look like. Okay, let's try another one. You ready? All right. This one actually gives you points to start and stop at, okay? So we're going to let v be the vector. I've got another one that's not bolded. V be the vector from the initial point, P1, to the terminal point, T2, and P2, excuse me, and we're going to write the vector V in terms of I and J. Okay? So what this is telling you, we don't have to draw a picture, though you could if you wish. If you want to draw this in the coordinate plane because they're giving you order pairs, feel free to do that. But what they're telling you is that you start here with the x values and you end here with the x values. So if you start at 2 and you end at -6, how far have you gone? 8. And you've gone 8 in the negative direction, right? Because you started at positive, you ended negative. So in particular, all you're doing is taking the first value, because that's the initial point. I think I said it. No, I did it. Sorry. The initial point, there you go, minus the terminal point. So you start with the terminal point, subtract the initial point. Sorry. Said it backwards there for a second. So it's where you end minus where you began. So we started at -6 and we ended at 2. So it's minus the initial point. And this is the I direction. So we're going to put it with an I hat or an I bar on top. We're going to do the exact same thing that we did for our J component. We're going to do it for our J component that we did for our I component. So we end at 6 and we started at -5. So we end at 6, which means there's a 6 here. And we started at -5, so this is minus -5, right? But think about it. If you go from -5 to 6, how far have you gone? 11, right? You've gone 11. And this is the J direction that we've gone. So if we are having this vector, and this vector is defined in our directions as vector V, this is how we find it. So this would be the -8, I. And then y'all just told me, I left off parenthesis, and it's 11J, like so. Okay, so jot yourself down a note because we didn't actually write down directional on this one. It's always terminal minus initial. That's the order. If you do it backwards, you're going to get the right values. You're just going to get the wrong signs. The signs are going to be flipped. Okay, so if you're getting something wrong and you're like, I know I subtracted that right, just double check to make sure that you put the order in right, okay? Because that's a common mistake. All right, it gets even better. This says U minus V. So they tell us vector U is 2I plus 5 minus 5J, excuse me. They give us a value for V, and then they say the vector W is -I minus 6J. When they're asking us to find subtraction, addition, scalar multiples, which we're going to do a couple of these, it's going to look just like algebra. So this says vector U. Well, vector U is 2I minus 5J. So we just write it in. Minus. And then vector W is -I minus 6J. Like so. Everybody good so far? And you literally combine like terms. Okay, now we do have a negative here to distribute, so we'll do that first just for carefulness. So this is 2I minus 5J, and then I have plus I and plus 6J. And if I combine like terms, what do I get? 3I plus J. Okay, so while this homework will not be due next time, it'll be due on Monday. It's going to look like a lot of problems. And the reason it's going to look like a lot of problems is because they're fast. Are y'all with me? So do not freak out when you look at the assignment and you're like, oh my word, what is she thinking? This is what I'm thinking, is that the problems work very, very quickly. Okay, let's try one more and then we're stopping because it's a good spot. All right, this one has 4W minus 3V. So what do you suppose happens with the 4 and the 3 at the beginning of those? They multiply, right? That's it. They're scalar multiples. So I'm going to write this in just like if I were substituting something in with an algebra equation. My W is on this one negative I, same as the last one, minus 6j, minus 3, and then vector V is negative 3I plus 7j. And we're going to multiply them through, right? Just distributing. So as I distribute these in both pieces, I get negative 4I, negative 24j. Notice every time you're writing the i's and the j's, they should have those hats on them or those bars on them atop, okay? And in fact, I think that if you don't do that, my math lab is probably going to fuss at you and give you wrong answers. So be careful. Something else, I could be wrong on that, but I'm pretty sure that's the case. We'll distribute the next one. So then I have plus 9I. My eyes are getting sloppier as I go. I. And then minus 21j. All right, how many i's do I have? 5. There's 5 i's. How many j's do I have? Yikes. Negative a bunch. How many? 45. Yeah. Negative 45j. Okay, the last thing that we have to do in this section are called unit vectors. We're going to push pause right there so that we can do that next time. And then we will start and probably finish 4.4. We'll see. I don't really want you to have more than one assignment due on a given day, so we might spread that out just a tiny bit on purpose so that that doesn't happen, okay? Have a great couple days.